like, All right. Good morning, everybody. Welcome back to our final stretch of the semester. So we will have this week and next week of classes, and then the week after that, it's going to be the final exam. I posted on Canvas an announcement containing a worksheet that will prepare you for the final exam. We will talk more next week on Thursday about the details of the final exam and how it will be done. Okay, so for this week, we must finish this chapter and hopefully advance to the next one on Thursday. So let's start here with some quick announcements. For this coming Thursday, we will have our in-class assignment. So I will give you a little bit more time to finish it like we did last time. And that will be the last in-class assignment that we will do for this semester. So be ready for the in-class assignment. Okay, so let's do here a quick recap about what we are seeing for this chapter. So the goal here is to draw Lewis structures of covalent compounds. Remember that we can always use the Clark's rule to figure out if there are only single bonds or if there is a double bond or even triple bonds. Okay, so we are going to compare X, and X is 6 times the number of atoms that are non-hydrogen atoms plus 2. And we are going to compare X with the number of all the valence electrons from the compound. If X is equals to the number of valence electrons for the compound, then we only have single bonds, okay, in the compound. If X minus the number of valence electrons is equals to 2, then you need one double bond. And if X minus the number of valence electrons is equals to 4, then you need two double bonds or one triple bond. Okay, so let me show you something really quick that might help you deciding how many bonds an atom can make. So remember that hydrogen will always make one single bond to fill the duet, and that's the capacity of hydrogen, so we don't need to cover that. And let's shift our attention to elements from group 14, 15, 16, and 17. For that, I will switch to my other screen here. Okay, so when we talk about elements from the group 14, I'm going to represent them as an X, just a random symbol here. And if they belong to the group 14, it means they have 4 valence electrons, and each electron is going to be represented by a dot. Therefore, they need 4 more electrons to fill out the octet. So what's the maximum number of bonds that an element from the group 14 can make? Think about that. 14 means they have 4 electrons in the valence shell. To achieve 8, you need 5, 6, 7, and 8. So that means any element from the group 14 can make a maximum of 4 single bonds, or any combination of 4 bonds. Okay, so for example, 1, 2, 3, and 4. So that's also possible, or even 1, 2, 3, and 4. Okay, so what I'm trying to show you here, that elements from the group 14, they make a maximum of 4 covalent bonds. They may be all the 4 single bonds, or a combination of 1 double bond, 2 single bonds, or 1 triple bond and 1 single. Okay, so with this same idea, elements from the group 15, they have 5 electrons in the valence shell. Therefore, they need 3 more to achieve 18. So same idea here, 5, 6, 7, and 8, and there will be a lone pair here. So again, a maximum of 3 single bonds, or a combination of 1 double bond and, for example, 1 single bond, or even 1 triple bond. Okay, the maximum number of covalent bonds under ideal circumstances is 3. We can use the same idea for elements from the group 16. 6 electrons in the valence shell, 1, 2, 3, 4, 5, and 6. So again here, I'm representing X, 6, 7, and 8, and 2 lone pairs. Okay, so a maximum of 2 single bonds, or even 1 double bond. Okay, so elements from the group 16, they will make a maximum of 2 covalent bonds under ideal circumstances. Okay, so we will see that there is an exception for this rule. And finally, group 17, 1, 2, 3, 4, 5, 6, and 7. So it's super close to 8, 7, 8, and that will do it for group 17. So therefore, elements from the group 17, they usually only make 1 single bond in most of the compounds. Okay, so remember, hydrogen, 1 single bond. Group 17 usually also 1 single bond. And then group 14, 15, and 16, they are more versatile. And you can use this idea here to try to figure out the number of bonds in the central atom with the Clark's rule that will guide you through the correct structure. All right. So of course, for every rule, there is always an exception, and that's what we are going to see right now. Okay, so the problem here is when we start investigating compounds, especially from phosphorus, uh, they can form this structure here with phosphorus bonded to 5 chlorines. Okay, so let's give you a couple minutes and then try to figure out what would be the structure. So remember to follow the instructions here. Count the total number of valence electrons, account for charges, choose the central atom, and then distribute the electrons among the atoms to fill the octet. And we are here talking about phosphorus, group 15, and chlorine, group 17. Okay, so start with the central atom, distribute the other atoms around it, connect them with single bonds, use the remaining electrons to fill the octet from the atoms outside the central atom, and then if there is anything left, that will go to the central atom. Okay, let's think about this problem for a couple minutes, and then we will do it together. Okay, let's try to figure out the Lewis structure of for PCl5. Okay, so the first step that I will take in order to solve this problem is to count the total number of valence electrons. Phosphorus belongs to the group 15, therefore it has 5 valence electrons. Those 5 valence electrons will be used in the covalent bond to form the compound PCl5. And chlorine belongs to the group 17, therefore 7 valence electrons, and we have 5 chlorines. That gives us a total number of valence electrons equals to 40 electrons, or 20 pairs of electrons. Okay, so 20 pairs of electrons will be used to make all the covalent bonds needed, and to complete the octet for all the elements in the structure. So the strategy here, now that you know the number of total electrons that you have, is to pick the central atom. Okay? The central atom is usually the larger one, and usually the atom with the lowest number in the structure. Here, there is only one option, and that's phosphorus. So that's going to be our central atom. And now I'm going to surround phosphorus with 5 chlorine atoms. Okay. Doesn't matter where you put them, it is random for now. 5 chlorine atoms, and then let's connect the central atom to each atom using a single bond. Okay? Single bond. For each single bond, we spend 1 pair of electrons. So let's mark here that these electrons are being shared between phosphorus and chlorine. Okay, so the pair now belongs to both atoms. Just to make the single bonds, we spent 5 pairs of electrons. 1, 2, 3, 4, and 5. Therefore, there is still 15 pairs of electrons remaining. Those 15 pairs of electrons remaining will be used to fill the octet of first the atoms that are outside the structure. Okay, so chlorine, this chlorine on the top is the one that I'm going to start, has 2 electrons. To fill the octet, we need 6 more. 1, 2, 3, 4, 5, and 6. Now, the chlorine on top has 8 electrons, so the octet is filled. So let's move on to the next one, and I will follow the clockwise order. Same thing, 1, 2, 3, 4, 5, and 6. Now, the chlorine on the left side has 8 electrons as well, and we move throughout the structure to fill out the octet for all the atoms that are connected to the central atom. Okay, once we did that, now we count again how many pairs of electrons we spent. If there is anything remaining, that will go to the central atom. Okay, so we had 15 pairs of electrons remaining. For each chlorine, we spent 3 pairs to fill out the octet. 3, 6, 9, 12, 15. Okay, therefore we have 0 electrons remaining to be distributed in the structure. So we used all the electrons. You always have to use all the electrons available. This structure can be also represented using this notation. Okay, so each covalent bond has a solid trace, and I would like you to always show me the non-bonding pairs in the structure, because that's going to be important in the future. Okay, so remember that the pairs that are not being shared, those are called lone pairs. Okay. So we saw here that each chlorine has 8 electrons now in the valence shell. Therefore, the octet is filled. Chlorine is stable. Let's count how many electrons does the phosphorus have. Okay. So each bond is 2. So we have 2 4, 6, 8, and 10. So in this structure, phosphorus has 10 electrons in the valence shell. Okay, so more than 8. The next question is this compound even possible to exist? Is phosphorus capable of having more than 8 electrons? Is this even stable? So let's see. Okay, so let me switch to the other screen. All right. So we figured out the structure of for PCl5. In this structure, somehow phosphorus ended up with 10 electrons in its valence shell. That's a violation of the octet rule. So the next question is this compound even possible to exist? That's the worst part of this kind of settings. I feel like I ask the question to myself. Now let's see if it is possible. Oh, there we go. It is possible. And I even took a picture from my lab here. PCl5, it does exist. It has phosphorus bonded to 5 chlorine atoms, and it is this very nice creamy color powder, a very reactive compound, but it does exist. And now it's a good point to introduce some exceptions to the octet rule. Some elements, they can expand the octet and accommodate more than 8 electrons in the valence shell. Those elements are any element below the third period of the periodic table. So I'm showing here in red. Those are all the elements that are capable of expanding the octet and accommodating more than 8 electrons in the valence shell. So how does that happen? So let's take a look here at the energy diagram. So you start here with the shell 1s. This is the most stable one. Then go to the 2s, 2p. So those are the next ones to be filled. And when you move on to the third period, now you have the 3s, 3p, and look here what happens with the 3D shell related to the 3P shell. So now the energy of the 3D shell is almost the same as the 3P shell. Therefore, elements below the third group can expand the valence shell towards the 3D shell, can use the d orbitals to make covalent bonds, okay? So instead just using the s and p orbitals, now I can expand to the d orbitals because the energy is similar to the p orbitals in the third period and after that. And the excess of electrons will be accommodated in the d orbitals. And that's the octet expansion, okay? And although is an exception to the octet rule, it's very common to find compounds that have more than 8 electrons in the valence shell. And remember, the only elements that are going to be capable of doing that are the elements from the third period and below that, because the energy of the d orbitals is very close to the p orbitals. And that is called hypervalence. All right. Okay, so now let's add one more thing to the Clark's rule that will help you um, to figure out uh, Lewis structures for covalent compounds. Okay, so we knew the first three already. So if X is equals to the number of valence electrons, then only single bonds. If the difference is equals to 2, you need one double bond. The difference equals to 4, then you need two double bonds or one triple bond. And if X minus the number of valence electrons is a negative number, then that's a clue that you have octet expansion for the central atom. Okay? So now you can use the Clark's rule and figure out if there is expansion of the octet for the central atom. All right. So let's do a practice then. Um, the question here asks you to draw the Lewis structure of the compound xenon F4. Okay, so noble gases, they usually do not uh, mix up with another elements because they are stable by themselves. However, when you move on to the heavier noble gases, you can force reactions and they are not so noble anymore. They will bond with other elements. And xenon F4 is the classic example of a compound, a covalent compound containing a noble gas. So what I would like you to do is to try to draw the structure, the Lewis structure for this compound. Okay, please show all the lone pairs. So let's give you a couple minutes and then I will start solving it. Okay, so let's see what we can come up for the Lewis structure of xenon F4. Okay, so let's start using the Clark's rule to figure out what's going on with this compound. So Clark's rule will always give us some sort of hint to start building the structure. And remember that we have to compare X to the number of valence electrons. And X is equals to 6 times the number of atoms that are non-hydrogen atoms plus 2. Okay, so let me, yes, that's correct. Okay, for this structure, we have 6 times 5 plus 2 for X. Therefore, X is equals to 32. And we are going to compare X with the total number of valence electrons for the compound. Xenon belongs to the group 18. Therefore, it has 8 electrons in the valence shell. And fluorine belongs to the group 17. Therefore, it has 7 electrons in the valence shell, but we have 4 fluorines in the structure. Therefore, the total number of valence electrons, according to my numbers here, is 36 electrons. Okay, so now we compare X with the number of valence electrons. So we are going to subtract X from the number of valence electrons, and that will give us minus 4. Okay, minus 4. If we come back here, oh, it's not here. So when you have a negative number, that means there is octet expansion for the central atom. Okay, so the central atom is going to have more than 8 electrons. And xenon is capable of that because it's below the third period in the periodic table. Okay, so now let's pick the central atom. Here, the only choice is xenon. Let's distribute the fluorines around the xenon. Doesn't matter where you put them for now. And let's connect the central atom to each fluorine using a single bond. Remember, each single bond uses 1 pair of electrons. So just to connect the central atom to the fluorine, we used 4 pairs of electrons. Therefore, we still have 14 remaining. Okay, so now let's use the remaining pairs of electrons to fill up the octet to the atoms that are bonded to the central atom. So fluorine has 2 for each single bond, 4, 6, and 8. Okay, so let's do that for all the other fluorines. So 8, and then 8, and then 8 for the last one as well. Okay, so just counting the 4 single bonds and the 3 lone pairs for each fluorine atom, we have used, let's see here, 4 pairs of electrons for each single bond, plus 3 pairs for each fluorine atom, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pairs of electrons to fill up the octet for for all the fluorines. So we have spent 16 pairs of electrons. Okay, so that means we have one pair left. Sorry, we have two pairs left, and the two pairs of electrons left will be just allocated to the central atom. Okay? So you just put the two pairs left in a random position for the central atom. So if you count the total number of electrons in the central atom, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so xenon has 12 electrons in its valence shell. Therefore, that means the octet is expanded for xenon. And that's what we suspected using the Clark's rule. Okay. So this structure is better represented when you use solid lines to represent the single bonds or any covalent bond. Show always the lone pairs in the structure, because that's going to be very important in the future. And in this case, we have two lone pairs for the central atom. And that's an example of a compound containing a noble gas. And it's a very classic example, the xenon F4. Okay, so let's go back here. Okay, so hypervalence is when an atom has more than 8 electrons in the valence shell. And we also can have the opposite, hypovalence. And that's very common when we have elements from the group 13, okay? Right here in the green, in the periodic table, that's the family of the boron. Elements from the group 13, they are stable with only 6 electrons in the valence shell, okay? They are hypovalent. An example here is the compound BF3. In this case, The fluorines have 8 electrons in the valence shell, 1, 2, 3, 4, 5, 6, 7, and 8. Remember, each covalent bond counts as 2 electrons. However, the boron has only one, oops, 1, 2, 3, 4, 5, and 6 electrons, and this compound is perfectly stable. So therefore, every time we have elements from the group 13, we may have hypovalence, which means 6 electrons in the valence shell is enough to stabilize the compounds. Okay. So now we have the regular octet rule and two exceptions. Hypervalence, more than 8 electrons in the valence shell, and hypovalence, only 6 electrons in the valence shell. And the three cases, they are capable of forming stable compounds. Okay, I think that's a good point for us to take a 5-minute break. So we will come back at 11:46 and let's talk about polarity. Okay. All right, so let's keep moving here. So now let's move on to polarity and electronegativity. Electronegativity is a periodic property, and as we know, a covalent bond where the electrons are shared is not perfect. Okay, so some elements they are very hungry for electrons, while other ones are not so hungry for electrons. Usually, small elements will be able to attract with more intensity the electrons in a covalent bond. So the most electronegative atom is fluorine, right here on the corner of the table, and that's followed by oxygen, nitrogen, chlorine, bromine, iodine, sulfur, carbon, phosphorus, and hydrogen. Okay, so therefore, in a covalent bond where where fluorine is present, this atom will attract the electrons shared in the bond closer to itself. And that's the meaning of electronegativity, is the ability to attract the electrons that are being shared in a covalent bond. Higher the electronegativity, higher the ability to attract electrons closer to the atom. And that's the order of higher electronegativity towards lower electronegativity. Von Klebrisk pH. Okay. Fluorine at the top, the most electronegative atom, and here at the end of the spectrum, hydrogen, one of the lowest electronegative atoms. And of course, you have all the other metals here that we are not going to cover, okay? So let's focus our attention to those elements that are present in covalent compounds, okay? Von Klebrisk pH. Fluorine, the most electronegative, and hydrogen, the least. Okay, so now let's correlate electronegativity with something called polarity. I want to first analyze the polarity of covalent bonds, and then we will expand that towards the whole compound. All right, so remember, in a covalent bond, usually the electrons are closer to the most electronegative atom in the structure. Okay, so usually the share of electrons is not equal. The electronegative atom will attract the electrons closer to itself. So I would like to analyze two compounds here, Cl2 and HCl. And let's try to figure out if in the Cl2 and in HCl, there is one atom that attracts more the pair of electrons compared to the other one. And from that, we will define polarity. So let me switch screens here really quick. All right, so remember that we will follow the von Klebrisk pH, being fluorine the most electronegative and hydrogen the least. So let's start here with the compound Cl2. There is only one single bond. Okay, so only one pair of electrons being shared. There is always a competition for this pair uh, when the atoms are present in the structure. Okay, so chlorine will compete with chlorine to attract more the pair of electrons. So let's think together. Chlorine pulls to the left, and the other chlorine pulls with the same intensity to the right. Will someone win this fight, or it will be called a tie? Chlorine has the same electronegativity as chlorine. Therefore, this is an example where the pair of electrons is equally being shared. And if we could take a picture of the electron density of this compound, we would see something like this. Okay, so very perfect distribution of the electron cloud. So there is no polarization of the electron in the structure, and the pair of electrons is being equally shared because chlorine has the same electronegativity as chlorine. They pull towards each other with the same intensity, therefore they cancel each other. Therefore, when there is no intense pull, no polarization, we call this chemical bond non-polar. Okay? So there is no winner here. Therefore, the pair is being equally shared. Therefore, this covalent bond is called non-polar. Now let's move on to the second example. Now we have here HCl. HCl is a covalent compound that has only one single bond, therefore only one pair of electrons is being shared. Now let's see if that bond is nonpolar or polar. Okay. To do that, we will use the von Klebrisk pH to figure out if there is a winner. Chlorine is right here, almost at the top of the order. Therefore, it pulls with a lot of intensity the pair of electrons close in the chemical bond. And oh my God, hydrogen is all the way to the end here. There is a pull, but the pull is really weak. Therefore, in this chemical bond, the pair of electrons is much closer to the chlorine than the hydrogen. Okay, so there is an atom that's winning the pair of electrons. Therefore, there is a pull and there is a concentration of the electron density closer to the chlorine. If we could take a picture of the electron density of the compound, we would see a little bit around the hydrogen and a lot around the chlorine because of the high electronegativity of the chlorine. Therefore, we call this compound polar. And to indicate the direction of the pull, or the direction that the electrons are being pulled in the chemical bonds, we represent that by a vector where the tail starts where we have low density and the head points to the side that we have high density. And I'm going to put a vertical trace in this vector, okay? And this vector is called dipole moment. And the symbol is mu, okay? So the tail of the vector will start at the point that we have low electron density, and the head is going to point towards the side that we have high density of electrons. And because we have a dipole moment in this chemical bond, we called it a polar covalent bond. And you can use symbols to indicate the atom that has high density and the atom that has low density. The density of electrons is going to be represented by delta. If we have a high density of electrons, that means we have excess of negative charges, therefore a delta minus. And on the other side, that you have low density of electrons is going to be a delta plus. Okay, so we can write HCl and delta minus at the chlorine and delta plus at the hydrogen. And that tells you that this compound is polar. Okay, so there is a polarity in the molecule. It's almost like a battery where you have a positive side and a negative side. Okay, the negative side is always located in the highest electronegative atom, and the positive side on the lowest electronegative atom. The polarity of the bond is going to be represented by the dipole moment vector. The vector starts in the atom with lowest electronegativity, and it points to the highest electronegative atom. And that's how you classify chemical bonds and also chemical compounds in polar and non-polar. Okay. So there is a correlation between polarity and uh, solubilization of compounds. If we take uh, chlorine gas that's insoluble in water, but HCl is freely soluble. And the same thing happens with bromine gas, Br2, also insoluble in water, but HBr is soluble. Why? Okay. So let's look first at the water molecule. So the structure of the water molecule is represented by this structure. So let's analyze if the bonds are polar. So oxygen and hydrogen are competing for the pair of electrons in the bond. Oxygen is much more electronegative than hydrogen. Therefore, there is going to be a dipole moment for the OH bond that points towards the oxygen. Okay. When we are talking about a whole molecule, we have to analyze all the vectors. And if the sum of all the vectors for each chemical bond is different from zero, the molecule is polar. So therefore, for water, the two vectors, they add up to each other, and there is a dipole moment, a resulting dipole moment different from zero, which means water is polar. The oxygen is the negative part of this dipole, and the hydrogens are the positive part of the dipole. Okay, so therefore water is polar, which means it will solubilize polar compounds. Cl, Cl, and Br, Br are both nonpolar, which means not soluble in water. However, when you replace one of the chlorines by hydrogen or one of the bromines by hydrogen, now you have two compounds that are polar, and therefore they will be soluble in water. So the rule of thumb is polar compounds dissolves polar compounds, and non-polar compounds dissolves non-polar compounds. Okay. All right. Okay. So now I would like to introduce the concept of formal charge. In the calculation of formal charge, the atoms are considered to have the same electronegativity. Therefore, electrons are equally shared. Formal charge will help us to choose among several structures which one is the most stable structure for a compound. And the rule of thumb here is that every time you analyze multiple possibilities for a compound, the most stable structure has the lowest formal charges on the atoms. Okay, so the atoms like to have close to zero formal charge. Double or triple charges are usually not stable, and if there is a negative charge, this charge has to be located in the most electronegative atom. How do we calculate formal charge? Very simple formula. It's going to be equals to the number of valence electrons minus half of the bonding electrons minus the non-bonding electrons. So let's here do an example for the compound PCl3. PCl3 has phosphorus in the center, bonded to 3 chlorines. The chlorines have 3 non-bonding pairs of electrons each. And then to fill up the octet of phosphorus, we have 1 non-bonding pair for the phosphorus. To check if this structure is stable, we will calculate the formal charge of all the different atoms in this structure. The stable structure will have neutral charges in all the atoms. Okay, so let's start calculating the formal charge for phosphorus. Remember that formal charge is equals to the number of valence electrons minus half of the bonding electrons minus the non-bonding electrons. Okay? So think about that. The number of valence electrons is what the atom started with after the bonding, and after the non-bonding electrons, how much is left for this element. So let's do that for the phosphorus. Phosphorus belongs to the group 15. Therefore, it has 5 valence electrons. So that's what phosphorus started with. Okay. So let's put 5 minus half of the bonding electrons. Each bond counts as 2 electrons. Okay, each bond counts as 2 electrons. Therefore, if we have one single bond, that's 2 electrons. If we have a double bond, that's 1, 2, 3, and 4, and so on. Let's see how many bonding electrons phosphorus has in this structure. 2, 4, and 6. So half of 6 minus the number of non-bonding electrons, if there is any. In this case, phosphorus has 2 non-bonding electrons. Therefore, we are going to subtract 2 here. And let's see the formal charge for phosphorus. Half of 6 is 3. Half of 6 is 3. 3 plus 2 is 5. 5 minus 5 is 0. Okay, oops. Therefore, the formal charge for phosphorus is 0. Now let's do the same thing for chlorine. Formal charge for chlorine is going to be 7, because that's the number of valence electrons for chlorine, minus half of the bonding electrons. So each chlorine, so you have to analyze it, each chlorine has only two bonding electrons. So that's going to be 2 plus the number of non-bonding electrons. For each chlorine, we have 2, 4, and 6. So that's going to be half of 2 is 1, plus 6 is 7, 7 minus 7 is 0. So therefore, the formal charge for chlorine, for the one on the most left side, is 0. If we look at the chlorine at the bottom, is exactly similar, exactly identical to the one on the left, therefore 0, and the one on, sorry, the one on the most left side here is 0 as well. Therefore, the formal charges for all the atoms in this structure is 0. Therefore, that means this structure is stable.
Professor, I have a question. I thought we were supposed to subtract the non-bonding
And
electrons.
that's the reason you have only single bonds and not something like that. Okay, so you can go ahead and calculate the formal charge for this structure, and you are going to notice that there are charges different from 0. Therefore, calculating the formal charges for all the atoms in a structure will guide you towards the most stable structure. And that's going to be really clear for the case of the sulfate. Okay. Now we have the possibility of multiple structures, and we have to decide which one is the most stable. And to do that, we are going to calculate the formal charge for every atom in the structure. The most stable structure has, if possible, 0 formal charges in all the atoms. We have to avoid double or triple charges because they are not stable. And if there is a negative charge, that charge has to be located in the most electronegative atom. So here let's draw all the possibilities for the structure of sulfate. Okay. So let's imagine that we have only single bonds. And I'm going to put the net charge here on the outside. And let's complete all the oxygens with 3 pairs of non-bonding pairs. So sulfur has 8 electrons in the valence shell, and all the oxygens have 8 as well. So apparently this would be a possible structure. We could come up with something like that. One double bond between one of the sulfurs, sorry, between the sulfur and one of the oxygens. So that's also a possibility. Also, we could have 2 double bonds and 2 single bonds. That's another possibility. Now, in this case, all the oxygens have the octet field. However, sulfur has an expanded octet, which is perfectly possible. And we could be really wild and come up with 3 double bonds and only 1 single bond. Okay. So which structure is the most stable? The calculation of the formal charge will tell us which one is the most stable. The preference is that the formal charge for all the atoms would be zero. Double or triple charges are not stable at all. If there is a negative charge, that has to be located in the most electronegative atom in the structure. And one more thing, the sum of all the formal charges for all the atoms has to be equals to the net charge of the compound. Okay? Therefore, for sulfate, the sum of the formal charges has to be equals to 2 minus. With that being said, I think that's a good point to stop, and we will come back and finish this chapter and start a new chapter. Okay, so I will see you on Thursday.
Thank you,